this lecture we are going to see maybe one example of application of conditional probability to a very interesting problem, and then maybe a couple of simple examples following that for binomial model and geometric model and things like that. Okay. So, let us get started. The example I want to talk about is called the birthday problem. Okay. It is a very popular problem in the in this area. So, you might want to search it on Google or something, and you will find a Wikipedia page which talks about it, and my presentation is very standard. It is based on this very standard ideas. Okay. So, the question that is asked here is, let us say you have a group of n people. Okay. So, the basic question they want to ask is, what is the chance that any two of them have the same birthday? Okay. So, that is the question. So, it is a sort of an interesting question. You have a group of n people, n could be any number 10, 20, 30, 200, 400, whatever. What is the chance excuse me, what is the chance that any two of them have the same birthday? Now, this is an interesting phenomenon. Maybe some of you have experience observing it. When as you grow up, when you are in classroom, you would have let us say 30 people, 40 people in a classroom, and you will see invariably there might be one or two people who have the same birthday. Okay, that ends up happening quite often, and there is a very interesting answer to this question. You can put a probabilistic model to model the birthdays of people, and then come up with a calculation which will show you this number, and there are very surprising answers to this number. So, for instance, one way to start this argument is to first say, suppose n is say 400. So, if you think about it, the number of different birthdays possible is 365, right. There are 365 days in a year. Maybe if you include the leap year and February 29th, you are going to get 366, right. So, there are only 365 possibilities, and there are 400 people. Okay. So, if you start assigning birthdays to each of these guys, you will have two people, at least two people who share the same birthday. Okay. So, in fact, this is very large. So, you imagine the number of people you need before two people will start sharing the same birthday is of this order, maybe 365, 300, 350, exactly. So, something of that order is what you naturally think. But it turns out surprisingly, so let me complete this. If n is 400, then with 100% chance, 100% chance of two people sharing birthdays, of at least two sharing a birthday, right. So, because there are just too many people, and this would work. Now, I will show you a probabilistic model, some sort of a uniform probabilistic model, where you will have some surprising results. So, it turns out if n is something like 70, then roughly the chance of having two people having the same birthday is 99.9. Okay. So, even for 70 people, it is almost certain that two people will have the same birthday, apparently, according to some probabilistic model that we will put down. Chance is of the same chance is 99.9%. So, you do not really need of the order of like 350, 400 people before two people start sharing a birthday. Even 70 people are enough, and the probabilistic model is basically uniform, and you will see it is a very interesting model, and it definitely works in practice. So, quite often this is true. So, if you have a class or a group of people which are 70 and you expect their birthdays to be very random, okay, you should not badly pick that group of people, then almost surely 99.9%, I mean it is a very high percentage, very high chance that two people will have the same birthday. In fact, much more interestingly, so supposing if n is 23, it turns out it is roughly 50% chance. So, even if you have only 23 people in a group with probability half, which is quite high, if you think about it, 50% chance that two people have the same birthday. Okay, so this is also something you can try. I mean, of course, with 23 people, it may happen that no two people have a birthday, it is only 50%, it is not very high, but 70 it becomes almost 100%. Okay. So what is this model, what is this interesting model that we have, and how does it work, and it turns out, like I said in the beginning, conditional probability plays an interesting role here. Okay. So let us define this probabilistic model. So I am going to have a okay. So in my model, the birthday of each person is independent and uniform. Uniformly likely to be any one of the 365 days in a year. Okay. Any one of the 365 days in a year. So this is the model. So what does that mean? So let us say we have n people and their birthdays are B1, B2, so on till Bn. Each B1 can belong to, I will simply number the days of the year from 1 to 365. Of course, you can argue I am approximating here, I am not looking at leap years and all that. So, we will just throw away people who are born on February 29. So, we are not going to consider that. We will just take 365 days of the year and we will say birthdays are equally likely to be anywhere there. So, in fact, you can bring in more complicated models, it only makes your life more difficult. So, this is easy enough. So, this is uniform. So, what does that mean? So, each birthday, so let me put Bi here to indicate this I could be from 1 to n. Every Bi, so right, every one of these birthdays can be either 1 or 2 or 3 all the way till 365. Remember 365 would be December 31st, 1 would be January 1st. Okay, so that is just the way of way in which I am counting the days of the year from 1 to 365. So, each of these is 1 by 365 in probability. This is 1 by 365, this is 1 by 365 all the way till here. So, now it turns out this may not be a very accurate model if you go by maybe biological or other considerations. This is apparently not very true, but for our model it is quite reasonable and it works. Okay. So, this is the model that we are going to have. This each Bi is like this, and they are all independent, as in B1 and B2 are independent events. Okay. So, this is also something important to consider. Okay. Is that okay? So, each birthday could be equally likely to be any one of the 365 days and they are all independent. Okay. So, in this setting I want to calculate that there is at least 2 of these birthdays are equal. Okay. That is the idea. Is that okay? Hopefully, you can see where the calculation will come from. So, let us see how to go about doing a problem like this. Okay. So, hopefully, the model is clear. Okay. So, the event, what is the event I am interested in? The event I am interested in is the event E, which is at least 2 of the birthdays are the same. They fall on the same day. Okay. So, it turns out this event, if you directly try to calculate the probability, it is not impossible, but it is going to be a lot more painful. So, quite often when you try to compute probabilities for a particular event, you should always think of the complement of the event, because in many cases the complement of the event might be easier to calculate. Okay. So, in this case also that is true. Let us look at E complement. What is E complement? No 2 people have the same birthday. So, this is what I am going to look at. So, no 2 people have the same birthday. So, each birthday is independent and uniformly likely to be any one of the 365. Okay, that is my model, and I want to find the probability that no 2 of them have the same birthday. They should all have different birthdays. Okay. So, that is the little calculation that we want to do here, and I mean you might see that this can be done using conditional probability. Okay. So, we first look at the first person's birthday. Okay. The first person's birthday could fall on any one of the 365 days. Now, given that first person's of the birthday has fallen somewhere, where should the second person's birthday fall? It should not be on the same day as the first person's birthday. It can be any one of the remaining 364 possibilities. Okay. What about the third person, given the first two persons' birthday were different? It cannot be any one of the two possibilities which were already there. So, it should be 363 possibilities. Okay. So, that is the way in which you can conditionally argue given each of the birthdays. Okay. So, let me try to write that down in a reasonable fashion. Okay. So, I am going to write the probability of E complement by conditioning on the first person's birthday. Like I mentioned, the first person's birthday can be any one of the 365 possibilities. Okay. It could be anything. I mean, my event of E complement, no two people having the same birthday, is not going to be false given any day for the first person. Now, given that the first person has a particular birthday, and given that the second person's birthday is independent of the first person's birthday, and conditioned on that, what are the favorable outcomes for me for the no two people having the same birthday? The second person should not have the same birthday as the first person, right. If he has the same birthday as the first person, my event is violated. Okay. So, it is not true. Second person should not have the same birthday as the first person. So, that becomes 364 by 365 possibilities. So, notice I have used both the fact that no, I have used the fact that the two birthdays are independent. So, this is for the first person, this is for the second person. Okay. So, I have used the fact that the birthdays of the two people are actually independent, and I have also used conditioning. I have first written the event as a combined event of birthdays of all these people, then I am looking at the first person's birthday, conditioned that the first person's birthday was a particular date, what are the favorable outcomes for the second one, okay. And then I can keep on going. Okay. So, what about the third person? Third person can be born on any one of the remaining 63 possibilities, and so on. Okay. So, you can go on till 365 minus, so this is for the third person. So, for the nth person, you will have n minus 1 here, okay, by 365, right. So, how did I get n minus 1 here? You can think about it. For the second person, I have 365 minus 1. For the third person, I have 365 minus 2. So, for the nth person, I should have 365 minus n minus 1. Okay. So, this is the probability that no two people have the same birthday. Okay. So, think about how conditional probability and independence together are helping you to build up the probability for this event in a very simple manner. Okay. So, you can also do it in so many other ways. So, for instance, you can look at the total number of outcomes. Okay. The total number of possible birthdays for n people is 365 power n. Okay. So, that is the total number of outcomes. What is the total number of favorable outcomes? Outcomes in E complement, that will be no two of them should repeat. The first one can be any one of the 365 possibilities, next one should be 364, next one should be 363, so on till 365 minus n minus 1, right. So, that is the idea. Is that okay? So, the same thing happened here, okay, but if you use conditional probability and independence like the way I showed you, you can directly write down. Okay. So, this is the probability of E complement, that no two people have the same birthday. So, what is the probability of E? That at least two people share a birthday. It is 1 minus probability of E complement. Okay. And now you can do a calculation for different n. You can go ahead and calculate this. You have to be a little bit careful. I would suggest the way you calculate this, it is best to write it like this. The first one is just 1, the second one is 1 minus 1 by 365 times 1 minus 1 by 2 by 365, sorry, so on till 1 minus n minus 1 by 365. Okay, you write it like this and then do the multiplication and find the probability, and you will see surprisingly for n equals 23, probability of E is roughly about 0.5, and for n equals 70, probability of E is roughly about 0.999. Okay. So, this is the result for the birthday problem, quite a simple calculation at the end, but it is a little bit surprising in the way you interpret it. So, in fact, even the birthday problem, the way it is framed, the model that I have built here is actually the same as balls on bins. Okay. Where are the bins, where are the balls? There are 365 bins, each representing one day of the year, and you have n people. These are the n balls that I am throwing uniformly and independently at random into these bins. And the event E, at least 2 of the birthdays are the same, asks, are there at least 2 balls in any one of the bins? Okay. What is E complement? No 2 people have the same birthday. All the bins have only either 1 ball or 0 balls. That is the E complement, and you can do it in this fashion. Okay. So, if you have just 23 balls and you are throwing them into 365 bins uniformly and independently, you have a 50% chance that 2 of them have the same. One bin has 2 balls, 2 balls went into the same bin. Okay. It is a bit unreasonable in some sense, but it's that is the calculation in this model, uniform independent model, that is the calculation. Okay. So, once again it is a nice illustration of conditioning on the sequence of events, conditioning on the previous event, next event and all that, and using the independence of different things to come up with this argument. So, you can see so many nice results one can derive in this fashion. Okay. So, hopefully this was an illustrative example for you. One more keeping up with this balls in bins example, I also want to show you one more nice way of thinking about this binomial model. So, if you look at balls into bins, okay. So, if you are throwing let us say 10 balls into 5 bins, okay, 5 bins, 1, 2, 3, 4, 5, okay, you are throwing 10 balls into 5 bins. I am interested in a success event, which is in fact ball went into bin 1. Okay. So, I am throwing this ball, I am going to count as success if the ball went into bin 1 and failure if it went into anything else. So, the probability of success is actually 1 by 5. Okay. So, number of successes is what? What is the number of successes? It is actually the number of balls in bin 1, right. Okay. So, this experiment is actually, if you were to only worry about the number of balls that got into a particular bin, or say for instance bin 1 here, this is nothing different from some sort of a coin toss and counting the number of heads, except that instead of probability of heads and probability of tails being half each, probability of success is 1 by 5. Okay. So, if you were to count the number of balls in bin 1, you once again have a binomial model. With P, which is probability of success, being 1 by 5. Okay. So, this binomial model this way arises in very many interesting situations. Anytime you want to count whether you had a success or not in a particular attempt and you want to count the total number of successes, the binomial model naturally arises. Okay. So, I want to leave you with one intriguing question about the geometric model. We will come back and look at it a little bit later on. The geometric model usually talks about the time of your first success. Okay. So, it turns out one can define first success in a slightly more complicated way to make the problem more interesting. So, for instance, supposing you have a repeated coin toss, repeated toss of a fair coin. Okay. So, you might define success as the first head. So, that was an example, it is a very classic example for the geometric model, the probability that the time at which you have the first head. Or you can also define it in a slightly more complicated way, you can think of a probability of having the second head. Okay. So, these are all very popular models. So, I am going to talk about a model here which is slightly more intriguing and more difficult. So, success I am going to define as 2 successive heads. This model for success you can immediately see is a little bit more complicated. So, what do I mean by 2 successive heads? I keep tossing a coin, if I get 2 heads in a row I can stop, no, I have succeeded. Okay. So, the kind of question that would ask is what is the probability that you will have the first time 2 successive heads come is at the particular position. So, for instance, so you are tossing a coin. So, let us say you have your sequence of tosses. So, the first toss, second toss, third toss, fourth toss, fifth toss and so on. So, you will have a sequence of heads or tails. So, supposing so if you could have heads here, okay, in which case you will stop. Okay. So, what is the probability of this? Probability is 1 by 4. Okay. What is the probability that the first time you have 2 consecutive heads is in the second and third position? Okay. So, you should have consecutive heads in the second and third position. You should not have consecutive heads before that, which means it should be a tail, and that probability is 1 by 8. Okay. So, hopefully you can see where it is going. So, what about first time 2 consecutive heads occurred is 3 and 4. Okay. So, hopefully you can see. So, I am tossing a coin repeatedly. When I get 2 successive heads I stop. Okay. So, first question is what is the probability that you will stop at the second toss. Okay. So, first 2 should be heads. So, you will stop at the second toss. What is the probability you will stop at the third toss? Second and third must be heads, and you should not have the first also as heads, because then you would have stopped at the second one, right. So, this is THH and that would be 1 by 8. What about the probability that you will stop at the fourth place was a little bit more complicated now, right. So, you can have in the first 2 tosses, right, you could have for instance TT, right, you can have TH, you can have can you have TH, I am sorry that was wrong, you can have TT, you can have HT, okay. You cannot have any other possibility, okay. You cannot have for instance TH. If you have TH, what will happen? You have had HH here, you would have stopped at the third. So, this is actually not possible, okay. So, the probability here of these 2 things happening, so let me maybe draw a line here to indicate that this is ended. The probability of these 2 things happening, it could be TTHH or HTHH. So, that is 1 by 16 plus 1 by 16. So, that probability is 1 by 8. So, by the fourth toss you already have half the probability. So, what happens if you go to the fifth toss? So, maybe I should draw this a little bit below. Okay. So, if you want to look at 2 consecutive heads by the fifth toss, you would have HH here, and what are the various things that are possible here in the first 3 tosses? You have to look at all those possibilities. You could have TTT, or you could have THT, right, and you can't have THH, you can have HTT, that is it. These are the 3 possibilities, right. So, these are the possibilities under which you can have 2 consecutive heads appearing only in the fifth place. So, that probability is already, this each one of these is 1 by 32 in probability. So, you have 3 by 32. So, you see the probability is dropping quite drastically, and it is not really very easy to compute. So, in fact, what is the thing for that you will have a success at the nth toss, and you will have to stop at the nth toss? N minus 1 and n have to be HH, and in all these guys including the n minus 1th toss, you should not have HH anywhere. Okay. So, it turns out computing these kind of things is quite tricky, it is not very easy. Okay. So, this is not really a pure geometric model in the sense, why is that happening? Why did this happen? Because this is not a pure geometric model, right. Your success in one position, a second success in the next position are not independent. Okay. So, geometric model applies when you have a sequence of events, they are all independent and you define success based on one event. Now, what happens here is you are repeatedly tossing a coin and you are defining a success event based on 2 events, and that complicates everything. Okay. So, once you have 2 events, successive events, because the probability, the event that you succeed at the second toss and the event that you succeed in the third toss now end up being related, okay, and you have to count the successive heads very, very carefully, and the computation becomes a bit more difficult. Okay. So, it is not very difficult or impossible to calculate this exact probability, but it is much more challenging. Okay. Geometric model does not apply in this case. Okay. So, why does the geometric model does not apply? because success at nth trial and success at n minus 1th trial are dependent. Okay. So, one needs to be careful, and also in any example that you come up with, you should be aware that under what conditions the model applies and what condition the model does not apply. Okay. So, dependence is always a situation that you have to take care of very carefully. Okay. So, that is the end of this lecture. In the ensuing lectures, we will start looking at random variables. You will see Professor Arvind's lectures explaining what a random variable is and different types of random variables, and I will come back and do some examples of those random variables as well. Thank you very much.